Welcome to the session on Laplace transform. The Laplace transform is used to produce transfer functions for the elements of an engineering system. These are represented in diagrammatic form as blocks. The various blocks of the system corresponding to the system elements are connected together, and the result is a block diagram for the whole system. By breaking down the system in this way, it is much easier to visualize how the various parts of the system interact, and so a transfer function model is complementary to a time domain model and is a valuable way of viewing an engineering system. The definition of Laplace transform is: the Laplace transform of a function f of t defined for all real numbers t greater than or equal to 0 is the function in S, which is denoted as capital letter f of s, and is defined as f of s is equal to integral 0 to infinity e raised to minus st into f of t dt, where here S is a complex number frequency parameter. That is, in order to get the Laplace transform of a function f of t, we just multiply the function by e raised to minus st, and we integrate this product e raised to minus st into f of t between the limits 0 and infinity. The Laplace transform takes a function of a real variable t to a function in S, that is f of t. The Laplace transform transforms the function f of t into another function f of s, where s is a complex variable. To denote the Laplace transform of f of t, we write L of f of t. That is, L of f of t equal to a function in S, which is equal to integral from 0 to infinity e raised to minus st f of t dt. As this integral is an improper integral, the restrictions may need to be placed on S to ensure that the integral does not diverge, which is the condition. Now we shall discuss the Laplace transform of some elementary functions. First one is the constant function. Consider the constant function f of t is equal to k, where k is a constant. The definition of Laplace transform is L of f of t, which is a function in S, which is defined as integral from 0 to infinity e raised to minus st into f of t dt. Now, by this definition, we have L of k, here f of t is the constant function k, which is equal to integral from 0 to infinity e raised to minus st into, here f of t is k, dt. K can be taken outside of this integral, that is k into integral from 0 to infinity e raised to minus st dt, which is equal to k into e raised to minus st divided by minus s between the limits 0 and infinity, which is equal to k into, when we apply this infinity for t, this term e raised to minus s infinity, that is e raised to minus infinity, which tends to 0. Therefore, here k by this minus s can be taken outside in the denominator. K by minus s into e raised to minus infinity tends to 0 minus e raised to 0. When t equal to 0, this term is e raised to 0, that is 1. This is equal to k by s. That is Laplace transform of a constant is that constant divided by s. In particular, if k equal to 1, we have Laplace transform of 1 is equal to 1 by s. Now consider the function f of t is equal to e raised to at, that is the exponential function, where a is a constant. Then by the definition of Laplace transform, we have L of e raised to at is equal to integral from 0 to infinity e raised to minus st into e raised to at dt. That is equal to integral from 0 to infinity e raised to minus of s minus a t dt, which is equal to, on integration we get e raised to minus of s minus a t divided by negative of s minus a between the limits 0 and infinity. This is equal to, when t equal to infinity, this term is e raised to minus infinity, which tends to 0. Therefore, this is equal to 1 by minus of s minus a into 0 minus, when t equal to 0, this term will become 1. That is equal to 1 divided by s minus a. Minus of 1 by s minus a into minus 1, that is 1 divided by s minus a. This is the Laplace transform of e raised to at. Now consider the function f of t is equal to sin at. Then by the definition, Laplace transform of f of t is equal to, that is Laplace transform of sin at, which is equal to integral from 0 to infinity e raised to minus st into sin at dt. We know that e raised to I theta is equal to cos theta plus I into sin theta. Therefore, e raised to I at is equal to, that is we replace theta with a into t, we get cos at plus I into sin at. That is sin at is the imaginary part of e raised to I at. Therefore, we can write this as integral from 0 to infinity e raised to minus st into sin at is imaginary part of e raised to I at dt, which is equal to imaginary part of integral from 0 to infinity e raised to minus st into e raised to I at dt. That is imaginary part of integral from 0 to infinity e raised to negative of, here s, here minus a, e raised to negative of s minus a into t dt. On integration, we get this is equal to imaginary part of e raised to negative of s minus a divided by negative of s minus a between the limits 0 and infinity, that is equal to imaginary part of here negative of s minus a into t. When t equal to infinity, this term will tends to 0, that is e raised to minus infinity tends to 0, that is imaginary part of 0 minus, when t equal to 0, this is e raised to 0, e raised to 0 is 1, divided by negative of s minus a, no, not a here, negative of s minus I a, that is e raised to negative of s minus I a into t divided by negative of s minus I a, which is equal to imaginary part of 0 minus 1 divided by negative of s minus I into a, that is equal to imaginary part of 1 by s minus I a, which is equal to imaginary part of, we can multiply both numerator and denominator by the conjugate of s minus I a, we get this is equal to imaginary part of s plus I a, s conjugate of s minus I a is s plus I a divided by here s minus I a into s plus I a, which is equal to imaginary part of, this is s plus I a in the numerator divided by, in the denominator this is s square plus a square, s plus I a into s minus I a is s square plus a square, which is equal to, this is imaginary part of s by s square plus a square plus I into a by s square plus a square. That is this is the imaginary part, which is equal to a by a square plus a square. That is, the Laplace transform of sin a t is a divided by a square plus a square. If we replace this function f of t equal to sin a t by cos a t, we have, by the definition, this is L of f of t equal to L of cos a t. Here if we replace sin with cos, we get L of cos a t equal to e raised to minus I minus s t into, this is cos a t dt. From here we can write cos a t as the real part of e raised to I a t. Therefore, cos a t is real part of e raised to I a t. We can replace all the imaginary part with real part. Here real part of integral 0 to infinity e raised to minus s t into e raised to I a t dt, which is equal to real part of e raised to minus of s minus I a into t dt. This is equal to real part of e raised to minus of s minus I a t divided by negative of s minus I a on integration between the limits 0 and infinity, which is equal to a real part of, on applying the limits, we get real part of 0 minus 1 divided by negative of s minus I a, which is equal to real part of 1 by s minus I a, that is equal to real part of, we multiply both numerator and denominator by the conjugate of s minus I a, that is s plus I a. Therefore, this is equal to real part of s plus I a divided by a square plus a square, which is real part of s by a square plus I into a by a square plus a square, which is equal to s by a square plus a square. That is the Laplace transform of cos at is s by a square plus a square. Now we have to find the Laplace transform of algebraic function t raised to n. By definition, L of f of t, that is here f of t is t raised to n, Laplace transform of t raised to n is equal to integral 0 to infinity e raised to minus st into here f of t is t raised to n dt, which is equal to integral from 0 to infinity. Here t raised to n can be written as t raised to n plus 1 minus 1 into e raised to minus st dt. We have the gamma function, gamma n is equal to integral from 0 to infinity t raised to n minus 1 into e raised to minus t dt. This is the definition of gamma n. Consider this integral from 0 to infinity t raised to n minus 1 into e raised to minus at dt. This is the gamma function. Now we consider this integral. To evaluate this integral, we use the substitution at equal to some u, so that a dt is equal to du, dt equal to du by a. The limits are the same because when t equal to 0, u will become 0, and when t equal to infinity, u also equal to infinity. Therefore, this is equal to integral from 0 to infinity t raised to n minus 1 means here t from here t equal to u by a, that is u by a raised to n minus 1 into e raised to minus at, that is e raised to minus u, dt is du by a, which is equal to integral from 0 to infinity. This is u raised to n minus 1 divided by a raised to n minus 1 into e raised to minus u into du by a, which is equal to, here in the denominator a raised to n minus 1 into a means a raised to n. That a raised to n can be taken outside because the integration is with respect to u. Therefore, this is equal to 1 by a raised to n into integral from 0 to infinity u raised to n minus 1 into e raised to minus u du, which is equal to 1 by a raised to n into, comparing this with this definition, this is gamma n, that is integral from 0 to infinity t raised to n minus 1 into e raised to minus at dt is equal to gamma n divided by a raised to n. Therefore, we can write here, this is here instead of n, here it is n plus 1. Here e raised to minus 30 instead of a, it is s. On comparison, we get this is as 1 by s raised to n into gamma n. This is the Laplace transform of t raised to n. If n is a positive integer, we can write gamma n as n minus 1 factorial. Therefore, this is equal to 1 by s raised to, sorry, here instead of n it is n plus 1, means this is equal to 1 by s raised to n plus 1 into gamma n. For n is if n is an integer, positive integer, we can write gamma n as n minus 1 factorial. Therefore, this is equal to 1 by s raised to n plus 1 into n minus 1 factorial. This is the Laplace transform of t raised to n. Now, we have an important property, namely the linearity property of Laplace transform. It is Laplace transform of c1 into f1 of t plus c2 into f2 of t is equal to Laplace transform of, sorry, c1 into Laplace transform of f1 of t plus c2 into Laplace transform of f2 of t. This is the linearity property of Laplace transform. Here c1 and c2 are two constants, f1 of t and f2 of t are two functions of t. By the definition of Laplace transform, we have the left hand side is equal to, that is L of c1 into f1 of t plus c2 into f2 of t is equal to integral from 0 to infinity e raised to minus st into this function, that is c1 into f1 of t plus c2 into f2 of t dt, which is equal to integral from 0 to infinity e raised to minus st into c1 f1 of t, that is c1 into e raised to minus st into f1 of t plus e raised to minus st into c2 into f2 of t, that is c2 into e raised to minus st f2 of t dt. Now, we can split this single integral into two, which is equal to integral from 0 to infinity c1 into e raised to minus st f1 of t dt plus integral from 0 to infinity c2 into e raised to minus st f2 of t dt, which is the splitting property of integrals, definite integrals, which is equal to, we can take the constant c1 outside of this integral because the integration is with respect to t. Therefore, c1 is a constant, c1 into integral from 0 to infinity e raised to minus st into f1 of t dt plus, similarly this integral can be written as c2 into, that is c2 can be taken outside, c2 into integral from 0 to infinity e raised to minus st into f of t dt, which is equal to c1 into, by the definition of Laplace transform, it is this is Laplace transform of, here the function is f1 of t plus c2 into, similarly this is Laplace transform of, here the function is f2, that is L of f2 of t. that is L of Laplace transform of C1 into F1 of t plus C2 into F2 of t equal to C1 into Laplace transform of F1 of t plus C2 into Laplace transform of F2 of t. Now consider the function f of t as f of t equal to the hyperbolic sign sin h a t. We have sin h theta is equal to e raised to theta minus e raised to minus theta all divided by 2. Therefore, we can write sin h a t as e raised to a t minus e raised to minus a t divided by 2, and Laplace transform of sin h a t is equal to Laplace transform of e raised to a t minus e raised to minus a t all divided by 2, which is equal to this 1 by 2 can be taken outside into Laplace transform of e raised to a t minus e raised to minus a t. This is from the linearity property of Laplace transform, which is equal to 1 by 2 into Laplace transform of e raised to a t minus Laplace transform of e raised to minus a t. That is equal to 1 by 2 into, here the Laplace transform of e raised to a t is 1 by s minus a minus Laplace transform of e raised to minus a t is 1 by s plus a, which is equal to 1 by 2 into here s minus a into s plus a in the denominator, in the numerator s plus a minus of s plus a, which is equal to 1 by 2 into, one simplification, this is 2a divided by this is a square plus a square, which is equal to a divided by a square plus a square, which is the Laplace transform of sin h a t. We used the linearity property of Laplace transform. Similarly, we can find the Laplace transform of cos h a t, which is equal to s by a square plus a square. Now let me conclude this session. In this session, we discussed the definition of Laplace transform and some Laplace transform of some elementary functions. Thank you for listening this class. Have a nice day.